right, in the second part, we are looking at heat energy and specific heat in chapter 15. So we were talking about how temperature is the average kinetic energy of molecules. But there is other kinds of energy involved in molecules. Molecules can have both kinetic energy and potential energy. And so the type of potential energy, if you can imagine that there are atoms in, a matrix or something, so the atoms are in a crystal, and then you start heating them up. Well, they can vibrate in place. Okay, so when they are going to the extremes of their position, then they would have more potential energy. Then as they passed back through their normal position, they would have more kinetic energy. Then they would rock back to the other extreme and have more potential energy. So it would be like a pendulum swinging, right? Potential energy, kinetic energy, potential energy. And so that can be part of the energy also. But what is heat? Heat is energy that gets transferred. I just said, what if we heat up these atoms? Well, if we're heating them up, we're adding heat energy. And so heat energy is transferred from one object to another. And heat transfers because there is a temperature difference. So here we have some hot dogs that cooked. And you can see, of course, that these hot dogs, they've been turned over. And so we see those black stripes where they've been burned on the grill. And what's going on there is that the grill is better at conducting heat energy to the hot dogs than the air. And so those black stripes are where they've gained more heat energy. So heat is defined as the flow of thermal energy or heat energy due to a temperature difference. The natural direction, of course, is from the hotter object, the higher temperature object or substance, to the lower temperature substance. So heat travels one direction, okay, not several directions. Let's see. I don't have that picture I was looking for. Okay, so anyway, so let's say you've got your finger touching a chunk of ice. Maybe there's a nail in there to help conduct the energy. Well, which way is the energy going to go? Your finger's going to get cold, right? But cold isn't an energy. Cold is when you're losing energy. Your body feels cold, and cold is when the temperature goes down because of the loss of energy. The energy, of course, is traveling from your finger to the ice. Now, heat energy became part of the fields of the other kinds of energy that people were studying, kinetic energy of motion and potential energy, when they were able to prove that it was that they were part of the same thing. Okay, they were both types of energy. And so one of the person who figured that out was James Joule. And so his device here, you can see he's got some paddles in some water, and there is a weight that is allowed to fall down a certain distance. So it's potential energy, it's losing potential energy. That energy causes the spindle to spin, which makes the paddles turn, and that is transferring energy to the water. And so the water actually heats up. So if you just stir some water, you're actually adding energy to the water because you're making the molecules move faster. You're giving them kinetic energy. Anyway, so he was able to actually do calculations showing that the temperature change was proportional to the amount of potential energy that was lost. Now, one of the people who proposed this earlier than that was Count Rumford. And Count Rumford, if you ever have to do a biography on someone, he had a fascinating life. So in page 285 on your book, they talk about Count Rumford. But he was he figured it out when he was part of the army, and they were having to bore out cannons and they would get hot. In those days, people had this theory of caloric fluid. So most people said, oh, yeah, when you bore out the cannon, what you're doing is releasing the caloric fluid that's trapped in the molecules. And Count Rumford felt that no, it was because the boring, though they were grinding away at the cannon, that friction was producing the energy. So that was his idea. Now, Count Rumford went on to be a very colorful figure indeed. He was in the Revolutionary War. As it turned out, he was on our side, but he wasn't. It turned out he was a spy, and so fled to Europe, where he eventually became Count Rumford. Anyway, so yes, so a very adventurous fellow. Whereas Mr. Joule, not quite as adventurous, but actually there's some good stuff on him too. His life. All right. So the unit for heat energy is, the old unit is the calorie, and we still use that today as a scientific unit for heat energy. It does go back to that word caloric fluid, which has to do with heat. And but of course, we can also measure energy in joules. So a calorie, though, is defined as the amount of heat necessary to raise the temperature of 1 gram of water by 1 degree Celsius at 1 atmosphere of pressure. So 1 gram of water by 1 degree Celsius. How much energy does that take? Well, it turns out that takes 4.184 joules, and that is what 1 calorie is. Now, when you are thinking, okay, so a candy bar with 200 calories, that makes sense now. But actually, the candy bar calorie isn't this calorie. The candy bar calorie is actually a kilocalorie. And that is 1,000 little calories, so it's actually 4,184 joules. And so they write it with a big C to make it different from the little c for this scientific calorie here. So anyway, so it's called a kilocalorie or a big C calorie, and it can raise the temperature of 1 kilogram of water by 1 degree Celsius. Okay, so when you read your food packages, the C here should always be capitalized. Now, it doesn't look special because all of these things are capitalized like fat, but the calories is actually supposed to be capitalized because that is a kilocalorie. So this 80 big calories, food calories, 80 food calories is 80,000 little calories. So it can raise 80,000 grams of water by 1 degree Celsius. Why do we need all that heat energy? Well, all that energy because we want to keep our bodies warm. Our bodies only work if we're warm, right? You've heard of hypothermia and things like that. What happens to people when they get cold? They die because their bodies no longer work. Our biology is such that we have to maintain not just a moderate temperature, but a pretty high temperature. I mean, it's almost 100 degrees, which is often 80 degrees above room temperature. Why do we have to be so hot? It's so that our metabolism works. Our body is a bag of salt water that needs to work only when it's warm. So it's warm salt water. Okay, now another unit, of course, in the British system is the BTU, the British thermal unit, and that is the amount of heat to raise 1 pound of water by 1 degree Celsius. And so if you have an air conditioner or something, they'll often measure things in BTUs or BTUs per hour. Okay, now, specific heat capacity is the idea that we were just talking about how much energy it takes to raise 1 gram of water. That would be 1 calorie, right? 1 gram of water, 1 degree Celsius. But what if it's 1 gram of aluminum, or 1 gram of lead, or 1 gram of gold, or 1 gram of wood? Is it the same amount of water? I'm sorry, same amount of energy? And the answer is no. You would have different amounts of energy needed to raise the temperature of different substances. It's specific to the material. So if you were adding equal amounts of energy to different materials, like these bricks versus some water, one of them would get hotter than the other, and one of them would heat up faster than the other. So no, the temperature of each would not be the same. So different substances have different heat absorbing properties. And we call this the specific heat capacity, where we're talking about how much heat energy is needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. Okay, so here's some specific heat capacities of materials. And if you use kilocalories per kilogram, then that's the same as calories per gram. So you see that water down here is still 1. It takes 1 calorie of heat energy for 1 gram, or 1 kilocalorie of heat energy for 1 kilogram. But if you look at all the other materials, they are less than 1, much less than 1 usually. The only one that's close here is the human body, and that's because we are a bag of salt water. With a few bones stuck in. But anyway, we're about 0.83, but you can see everything else is much lower. So even ice, which is a form of water, is 0.5, and steam is also 0.5. Whereas something like aluminum is 0.22. It's 1/5. It takes 1/5 as much energy to raise the temperature of aluminum. So aluminum will heat up much faster than water. And in fact, everything on this table will heat up faster than water, right? Because they all have numbers that are lower than that of water. You look at something like copper, it's 0.092, which means it's close to 0.1, which means that it's 1/10 as much as the specific heat capacity of water. So with the same amount of energy, you could heat up maybe 10 grams of copper while you're only heating up 1 gram of water. Or you could think that copper will raise to 10 times the temperature. So anyway, so the specific heat capacity is called specific because it's specific to different materials, and heat, because we're talking about heat energy, and capacity, which I didn't write on this page, has to do with sort of that old idea about caloric fluid, how much heat energy can it hold? But it's still true. Does the energy that you put into a substance make the molecules move faster immediately so they start to heat up, or does it get stored inside the fluid? And water kind of stores its fluid, its energy, sorry. So the energy gets stored in water somewhat. And so the specific heat capacity, the greater it is for a substance, then the greater amount of energy to raise the temperature, as we said. And water has the highest specific heat capacity. It stores large amounts of heat. And we're going to talk about that more later. But one of the things that happens is somewhere like a beach, your feet are hot as you walk across the beach, and then you get in the water and it's cold. And the reason is that the water has a 6 times larger specific heat capacity. Right? Sand is only like 0.16. So basically the water would take 6 times as much energy to raise to the same temperature. So anyway, so the sand heats up during the day and the water stays cool. Okay, so there's a formula you need to know, which is based on the idea that to figure out how much heat energy is needed, you need to know how much mass there is, you need to know the specific heat capacity, and you need to know the amount of the temperature change. All of those three things tie together to tell you how much energy is going to be used. So the formula is Q equals mc delta T, where Q represents heat energy, M is the mass, C is the letter we use for specific heat capacity, but don't confuse it with speed of light, which is another place we use the letter C. Like E equals mc squared, that's speed of light C, not specific heat capacity C. And the temperature change is delta T, right? So we put them all together with this nice formula, Q equals mc delta T. All right, so let's do a problem. You heat 60 grams of silver from room temperature to 140 degrees Celsius. How much energy was used? Okay, so I need to find out a couple of things, right? I need to figure out the mass. That's 60 grams. And then I need from room temperature to 140 degrees Celsius. That's giving me the temperature change. And of course, you should know that room temperature, you can use 20 degrees Celsius. So my delta T is going to be T final minus T initial, which is going to be, it's being raised from room temperature. So that's the T initial. So I'm going to put the T finals 140. Okay, so my temperature change is going to be 120 degrees Celsius. And the other thing I need is the specific heat capacity of silver. So for that, I'd have to look on a list. If you'll notice, you have specific heat capacities for 5 substances on your equation sheet. Those will be the ones that will be used in the next test, okay, or on your quizzes. So they're on your equation sheet. So for silver, the specific heat capacity is 0.056. It's very small. Silver heats up very fast. 0.056. And that can be kilograms per, kilocalories per kilogram, or you can use calories per gram, which we're going to do in this case because our mass is in grams. And specific heat capacity of silver. So I'm just going to put S for silver. I could use Ag for silver. That's its chemical symbol. All right. And another thing about specific heat capacity, instead of saying the word every time, you could just call it the specific heat capacity, SHC. Okay. But for symbol, we just call it CS. All right. So then I'm going to use the formula. Q is mc delta T. And I've got my mass is 60 grams. My specific heat capacity is 0.056. And my temperature change is 120. And so just multiply those together. 60 times 0.056 times 120 equals 403. Okay, 403 watts. Well, if you look at the units, grams cancels grams, calories cancels. Oh, no, calories doesn't cancel. Sorry. Missing. Oh, great. I'm missing something. I forgot my calories degrees Celsius. All right. Take that back. Let's see. I'm going to erase that line, hopefully. All right. So going back here. Okay, grams cancels grams. And degrees Celsius cancels degrees Celsius. And I'm left with calories. All right, because we want to have heat energy in calories. Okay, so there we go. Okay, so anyway, so that's the way that works, but make sure you ask questions, especially about like the peanut problem in class. Specific heat capacity has a lot of different ways it can be used. So if you would like to go over more of those, we will do that in class. Here's one more example, but it's also simple in many ways. You've got 80 kilograms of water rising from 12 degrees to 42 degrees. And so since it's kilograms, we're going to use kilocalories per kilogram, which is the same number, 1, for its specific heat capacity. And we have a temperature change of 30 degrees, and there's our mass. So again, you just put them all together, but because you have kilograms of water, we just know that in the end, we're going to get kilocalories of energy. So this is going to be 2,400 kilocalories. Okay, and now if you wanted to know how much that was going to cost, we could figure out this in what are called kilowatt hours. We'll talk more about that when we get to electricity, but there are 0.00116 kilowatt hours per kilocalorie. And so 2.8 kilowatt hours, which often will only cost about 10 cents per kilowatt hour. So it'll only cost about 28 cents to heat your bathtub. Okay, so that's the end of this. We're going to go to the next section. Okay.